This is John Baker, and I am doing my final project on the identification of foreign language from speech. This is an important problem because voice user interface, or VUI, has become an important way of interfacing with technology. For instance, we have Amazon Echo devices, we have Google Home devices, and these are integrating with our phones. Cars are having integration with these, and one common complaint with all of these devices is that you have to set the user's language to the language that the main user prefers. So imagine that you're visiting another country and the country speaks, say, French, and you're an English speaker, and you walk into your friend's home and you try to use their Google Home or another one of their assistants, and it doesn't understand you. This project will take on that exact problem of being able to identify the language of the speaker. And this way, we could have use cases where these voice assistants or other technology could identify the language of the speaker at the time rather than having some preference set for that. So to give an overview of how we'll solve this problem is we're going to develop a convolutional neural network. This will be built with Keras, which is a library that sits on top of TensorFlow. We're going to take audio files and train with a large training set of audio files for the French and English languages, and we'll be able to classify the language of the speaker given a new audio file. The technology that I'm using is a Lenovo laptop. It is an i7 processor and has 16 gigabytes of RAM. I do not have a GPU. The software, I use Ubuntu Linux. We're using Python 3 and uh, TensorFlow 1.13, Keras 2.24. Labrosa is used to process the audio files, and we'll get into that in just a few minutes. So to do voice recognition, it takes a large amount of audio data. And another challenge besides having sources of this audio data is it works best if you get a variety of speakers. So thankfully, Mozilla has put together a common voice project for people who need large data sets of audio. For English, there's quite a bit of data. There's 22 gigabytes, and it features a variety of speakers, male, female, variety of ages and accents. The same with French. It's much smaller. It's 2 gigabytes, but it's plenty for our purpose here. They also support many other languages like German, Spanish. We're going to concentrate just on 2 languages here due to our constrained timeline. So what we do is we download the data, and the data has transcriptions along with it. So not only does it have the audio files, but it has the golden utterance of what the person said. We don't need these transcriptions, so what we're going to do is throw those away, and we're going to just label everything English or French based on their source data set. We're going to use 4,000 audio files, 2,000 English, 2,000 French, and we're going to use these for testing. We're going to use 1,000 audio files to test. I'm sorry, we're going to use the 4,000 for training and the 1,000 for test. And what we're going to do once we download this audio and separate out the 4,000 files and the 1,000 files, we're going to pre-process that audio, and we're going to uh, use just the MEL frequency Selbstrom coefficients. Now, that's a form of feature reduction with audio files because these coefficients have the main data that we're looking for, and it's a common practice within the use of audio files to do a feature reduction like this, either through MFCCs or fast Fourier transforms or something to get out the frequencies and not just rely upon all the data because it's just too much data in even a small audio file. So one of our instructions was to provide a small data set of about 20 megabytes. So I did this by saving out those MFCCs to NumPy arrays. And so in the Jupyter Notebook, you can take a shortcut to jump right down to the section that says reload the preprocessed data. And if you start from that point, it'll reload those files, those NumPy arrays that only contain the MFCCs for the training and test data. So let's go over the installation and setup of the data as well as the model itself. So to prepare the data, we need to download the audio files from Common Voice. The Common Voice web page makes you fill out a small form. It has an email address and two check boxes to agree to their licensing. And when you agree to those, you can get access to the URLs. So I've put the URLs here. They're S3 buckets on Amazon. And the English, like I said, is about 22 gigabytes. The French, 2 gigabytes. So you unarchive that into a data folder. So I made a directory called data, and I unarchive the English and the French. And when you unarchive them, it creates a directory structure. So under data, now we have EN and FR. And then each folder has another folder underneath it called clips, and that's where the actual MP3 files are located. Since we don't want to use all 22 gigabytes or all 2 gigabytes in the case of French, we want to just use a reasonable amount of files. I created a bash script which takes the top 2,000 out of each folder, the first 2,000 files, and puts it into a CSV file, and then the last 500 in each folder, and puts that into a separate CSV file. So the next thing that I did was I built a Python notebook called build test train. And what this does is it reads those CSV files that were created on the previous step for training and test, and it records the path of each file and then the label, whether or not it's French or English. So it creates two files out of those four files. So you had training English, training French, test English, test French. So what it does is it combines the training into one file and adds the label appropriately. It adds the testing into a second file and adds the label appropriately. The next thing in my Jupyter notebook is I read each of those CSV files, and then for each entry, I read the MP3 file in there and then convert it to its MFCC. And I use 32 coefficients because the MFCC, the library we use with Labrosa that extracts those coefficients, it allows you to say how many coefficients you want, and I went with 32. I got this number. I tried 11, I tried 22, I tried 50, and I settled down at about 32. Did some small test runs with the network, and I found that 32 was about optimal. The next thing that my code does is build the CNN and executes the training over 100 epochs. So let's talk about these last two steps in a little bit more detail now. The CNN is defined as follows. It has three convolutions, starts at 32, goes larger to 48, and then even larger to 120. Between each convolution layer, I have a max pooling layer, and this was in addition, I had gotten this network, as I had stated previously, I'd gotten this network from our homework assignment the last week, and it's the dead simple audio recognizer. But I made a few modifications. In his, he didn't have these max pooling layers here or the average pooling. He only had one max pooling layer. So I put the max pooling in each and ran some tests and found that it was better with this network layout. And and when you think about the fundamental reason for this is that what we want is we want to extract general features for each language, and that's really why we start with a small number of layers, 32, and we grow larger. Is what we're looking to do is start with a zoomed out picture of the visualization, and then we want to look at features in more detail as we move down the network. And so these max pooling layers will look for those maximum numbers in its layer or in its pool and extract those. And so we're looking for the most prominent features at each step. And so if we move on here, as mentioned, we started with this model from building a dead simple word recognition engine. And we're using the coefficients 32, and we keep adding the layers. One additional step was I added regularization. This helped make the training test steps a little bit closer, but as you'll see in the results, they still deviated sharply. So let's take a look at the results. So here's the code that I used to train the network. And so we can see that I used 100 epics and batch sizes of 50. And remember, the training data set size was 4,000, and the uh, the test data set size was 1,000. So that would be this validation data here. Okay. Here's our training results. So you can see that in training we get up to 100% accurate, but we know that that's probably overfit here on the training data because when we do the test validation runs, we're getting about somewhere between 60 and 70%. If you averaged out, you're probably around 65, 67 in that area. So this wide variation, as mentioned, I tried adding regularization. I tried to actually add other max pooling layers to try to draw this down and bring these closer, but I was unsuccessful in doing that. Once it was finished training, which took about 10 minutes, was able to make predictions. So using this Python code here, which takes a single file, and it predicts whether or not that is an English or French audio file. And so um, the results of predicting 3 French and 3 English files is actually 100% on this batch that we had, which I was surprised at. I thought, maybe we would get 5 out of 6 or maybe 4 out of 6 based on our out of sample in the training runs, but it actually got all of them. And listening to each of them, the audio is quite clear. I listened to all 6, and there's no background noise, and you can hear the speaker audibly. So they're good quality audio. So to summarize the results that I found, we had a CNN that was trained on 4,000 audio files. There was 2,000 French, 2,000 English. We're able to hit somewhere between 60 to 70% accurate in the training and test runs using 2 different languages. I've read other papers about this same subject. I did some research on it, and I included one here. And they did a very similar method using a CNN, and they were able to get into the 90% accuracy. Now, one thing that they did that we didn't do is they chained together a CNN and an LSTM, and this helped them to learn features of longer audio files. So our CNN, because I started with that one, the dead simple word recognition CNN, it probably has a weakness with multiple word inputs, and that's what all of our audio files are. They're short sentences, but they're not single words. So most likely our CNN is not achieving high accuracy because of the fact that it's sentences and not single words, and originally it was designed for sentences. But their combination of CNN like we have plus LSTM, they were able to get into the 90%. So that could be an enhancement to this for future research. Um, Another thing we could do is use all 22 gigabytes that we have of training data. That would no doubt help to find more variations within speakers, find more variations within the language, and help us to achieve higher accuracy. But as time permits, we were only able to get 4,000, although that's a good training sample size for this particular exercise. So that concludes our summary and our study of foreign language identification using a convolutional neural network.